Hello again and welcome back to my computer vision channel. Today we'll talk about DETR for Panoptic segmentation. So I've had videos about DETR before, that time focusing on object detection, and today I want to go back a little bit and see how the model might work for segmentation and what is segmentation and all of the questions that might arise because of that. And here's the plan for today. So we'll start with what is panoptic segmentation, what's the difference with instance segmentation and semantic segmentation, what metrics are used for panoptic segmentation. Then we'll look at CoCo dataset, the one that is used for most of the object detectors nowadays and the one that DETR was trained on. So do we have panoptic labels for CoCo? How do they look like? Then we'll dive into the actual DETR segmentation head. So once again, I have videos about DETR for object detection that explain the algorithm in detail. I have one video about the algorithm, another one about code reading. So today we'll not look at the actual transformer part of the model. We'll only look at the part that is actually responsible for pixel segmentation. And finally, we'll do the actual code read again of only the segmentation part. So we'll show a quick notebook on how to actually apply the model and read and debug into the code of the model itself. And then we'll look at the source code for DETR and how it is used for segmentation. And so let's start with the question of what is panoptic segmentation? And so it's easier to explain if I just show you the paper. So they have, at the very beginning, quite a nice example of what different types of segmentation there are. So first, segmentation, the word itself, meaning dividing the image into some sort of segments. And they can mean anything, but in computer vision, we usually talk about semantic segmentation. That is when we divide the image by the segments according to what is the semantic meaning of those pixels. So this is a car, a car, a car, this is a road, and then sky, and so on. And so in more strict terms, we usually call that classification. So we want to classify each pixel, give it some sort of label to what sort of object it belongs to. Slightly different task is called instance segmentation, where now, apart from just saying to what type of object the pixel belongs, we want to say to which specific instance of that object the pixel belongs. So we now want to distinguish car number 1, car number 2, car number 3, person number 1, person number 2, person number 3. And this task turned out to be actually much harder for neural networks, because for simple semantic segmentation, where you do not distinguish between instance types, you can just solve pixel classification problem. And with instance segmentation, it is now much harder because we have variable number of objects per picture. So we now have to keep track of all the different instance IDs that the model needs to output. However, with transformers, with DETR, this is actually solved pretty well and pretty elegantly. And finally, panoptic segmentation. So one of the problems with instance segmentation, as you can see from the image, is that it doesn't segment everything. So although we do segment different cars and people, there is no difference to sky and trees and road in this sort of segmentation. So panoptic segmentation was aimed to sort of unite the two tasks of instance and semantic segmentation. So we want every pixel on the image to have a notation. We want to distinguish classes of all the objects of everything that we see on the picture, as well as instances. And in this respect, this is a really, really important paper. So it came out in 2019. So it brings those two tasks together. And it is especially important because, for example, in old school semantic segmentation, it was most commonly used for the so-called stuff classes, where stuff is air, sky, tree, road, something that doesn't really have different instances, something that might not have specific boundary. And it is arguably quite important for applications like self-driving cars, when you actually need to know where the road ends and where the wall begins and so on. And then we also have so-called things classes, like cars, people, where you actually have car number 1, car number 2, car number 3. And so historically, these two tasks were not only solved by different models, they also had separate metrics, separate data sets, separate approaches, and so these two branches of science basically were diverging, and there is no one solution that will be good at both, and also no one framework to even assess that solution. So this paper tries to solve that, and I think it does that successfully. So nowadays, so it came out 5 years ago. By now we mostly talk about panoptic segmentation. So in this respect, the paper is successful. And so panoptic segmentation now unites these tasks. So it not only allows you to segment actual classes and instance IDs, it also allows you to uniformly assess models that deal with stuff and things. So stuff like air and grass and things like cars and people. So I definitely recommend to read this paper. I'll leave the link in the description. It's just called Panoptic Segmentation from 2019. And obviously we need some sort of metric to assess the quality of the models regarding panoptic segmentation. And the metric is called PQ metric, panoptic quality. And normally with metrics like these, you actually need to solve two problems. First problem is the matching. How do you match ground truth to predictions of the model? And second is how to actually get to the value of the metric for that. So this is an example of metrics for object detection. So imagine that we have an image with 2 birds, 2 bounding boxes, and the model predicted 3 bounding boxes. So to match one to another, we need to solve this problem. So we need to decide like how do we match them such that some sort of optimum is reached. And with actual PQ metric, everything is much easier. So what PQ does is it says that first, let's see at predictions, let's see which ground truth segments there are, and only consider it a match if it satisfies a threshold of 0.5 IUU. So if at least half of these intersect, we can consider it as a match. And so the ground truth segmentations are non-intersecting. So one pixel always belongs to exactly one segmentation. And from the two of these, it follows that only after applying the threshold, the matching is now unique. And so we don't really need bipartite matching. And this is a huge simplification on how the metric is calculated, how you can interpret it. So it's really nice. And this is how the actual metric is calculated. So imagine this picture. So you have sky, grass, dog, and 3 people. So this is the ground truth, this is the prediction. So first we basically decide on these matches. So in this case, we can see that most of the objects have intersection above 0.5. And then we perform the calculation of the actual number of true positive pixels, false negative pixels, and false positives. So in this case, we can see that one true positive is the intersection of these two segments predicted, and ground truth, the intersection of these two segments. Then this brown person is not predicted at all, so it's a false negative. And then the model detects some sort of person in here, which is not present in the image, so everything in this mask goes to false positives. And so the actual value of the metric is calculated like this. So it's a sum over all the classes of IUUs between predicted and ground truth divided by true positives plus false negatives. And it's easier to understand what that means if you just multiply and divide by the total number of true positives. So in this way, this first term, also sometimes called just segmentation quality, this is basically the mean IUU between predicted and ground truth objects. And then the second term, you might recognize that as F1 metric. So it's one variant that is that strikes a balance between precision and recall. That's called F1 metric. It's typical in analyzing the quality of classification. So the metric itself is pretty straightforward, pretty easy to understand. Couple of comments here. So first of all, we rely on IUU here, and it is averaged over all the classes. So one thing that helps with is if you have some sort of class imbalance. So if you have a weird class like a cup or an umbrella that is only present in like 0.5% of all the images in your dataset, since the averaging happens across the classes, that 0.5% of all the images will contribute in exactly the same way as any other class. You would still count all of those umbrellas with the same weight as everything else. Second, since we only rely on IUU here, it will work for small objects as well as for big objects. So even if your dataset, in terms of the actual number of pixels occupied, is dominated by, I don't know, elephants, you would still consider mice with the same weight because you only look at IUU, and so if your detector is not good at segmenting these small objects, you will have enormous penalty in terms of IUU. Alright, so we have our Panoptic segmentation task and metric. Do we have the actual labels for the dataset we're interested in, like CoCo? And the answer is, thankfully, yes, we do. So CoCo creators added the Panoptic class labels to the dataset. It actually happened in parallel to that Panoptic segmentation paper. So this is the paper called CoCo Stuff that came out in 2018. And so in this work, they basically added labels for extra classes, something like 50 extra classes, to cover pretty much everything on the image. So apart from people, boats, and stuff like that we already had in CoCo dataset for object detection, for example, new classes were added, such as sky, trees, walls, roads, and so on. And altogether, the new classes with the old classes cover pretty much most of the pictures that we see in CoCo dataset. So we have 53 extra classes, and some of them might look a bit weird. So for example, we have wall and wall brick, and also something called pavement merged. And this basically is trying to solve a problem of different annotators thinking in different terms. And this problem always arises when you have specific class labels. So someone will just consider a wall to be important, and then someone else will distinguish between a brick wall and a concrete wall and a metal wall, and then someone else might consider that to be too specific, and there is no one good solution. So, for example, one solution to that in the ImageNet dataset is to just create complete hierarchy of all the objects in the world. And so the full ImageNet dataset currently has like 22,000 classes, but obviously it's not the best solution because now you need your annotators to be aware of that specific classification, to be aware of that 22,000 classes, and to be able to distinguish one to another. So it's really getting quite hard at this point. On the other hand, if you just always go to the most general, you might miss some important details. And so what they did in CoCo Panoptic was strike some sort of balance. So they chose only the most frequent types of objects. And so that's why they have wall brick and I think wall concrete. And then for everything else, they just use the wall and similar to other objects. So they only created separate categories for the most common types of objects and stuff. And then everything else, they just united into this sort of merged category that unifies a lot of different objects types. So another problem that I think is worth mentioning, if I just go to the CoCo dataset explorer, is that sometimes there are a lot of objects on an image, and actually not all of them will have different instance ID. And again, this happens because it takes a lot of work to actually annotate all of that. And so the creators of CoCo dataset just decided that if there are too many objects on the picture, let's just give up. Let's just mark everything else as crowd. So this is a good example. We have something like maybe 50 people here, and we can see that there are labels on only for some of them. And then if you actually look at the data for this specific image, for everything else, it will just have one segment that covers everyone, one bounding box, and then it just says this is a crowd. And so this is a way to save some time on the actual annotation, and these actual objects will be thrown away from the metric calculation. They're typically thrown away during training. so as to not confuse your model. But this is not ideal. And for example, in a different model called Segment Anything, SAM from Facebook Research, that came out later than DETR, they use a different approach to solving the same problem, where instead of panoptic segmentation, they solve promptable segmentation, that is, given a point or a bounding box on an image, return the segment corresponding to that point. And to solve that problem, they actually created a semi-automatic data engine for annotations. And you can see in their paper, they have annotations for everything. So there are some pictures with thousands of different objects, and each of them has a different mask, different instance ID. But unfortunately, this annotation does not fall into the same, they don't even have class labels. And obviously you can't use it for panoptic segmentation, because for panoptic segmentation you actually need class labels. So this is like a different solution to the same problem. And this is how these panoptic images and labels actually look like. So this is the very first image from CoCo train dataset. And you can see that apart from the old objects and labels like bowl and orange, we also have new categories like food, other merged, and table merged, each with a giant bounding box covering pretty much everything. And then the actual pixel masks are represented as PNG image, where the color of the pixel encodes the object ID that you can then translate into category ID and instance ID of that object. Final thing worth mentioning regarding CoCo Panoptic is this papers with code leaderboard for panoptic segmentation, which shows the history of different publications of different models trying to solve the task. We can see the current state of the art, we can see what was state of the art in the past. That I consider a good tool for learning, because you can basically see the history, you can create a learning plan based on this leaderboard. And so at the very top we can see the model called Mask Dino. So this is definitely something that we'll talk about in future videos. And now let's talk about how data is actually used for segmentation. And so first of all, we now have extra classes, extra labels for our data set. So DETR for panoptic segmentation is trained from scratch on these new annotations. And the DETR for panoptic segmentation is trained on this modified version of the dataset with extra classes in the same setting as before. So it is trained to detect objects, it is trained to output bounding boxes and class labels, but it now becomes aware after training on this new dataset, it becomes aware of the new classes that exist. And so this is the architecture of the original paper. The DETR segmentation will use the same basic transformer as the main component of the model. So we'll have the picture being fed into a backbone like ResNet. It will be passed through encoder and decoder. The output of that will be a set of query embeddings, each of them then being projected into bounding box predictions and class predictions. And the only difference here is that now we have these extra bounding boxes for, in this case, water, that will cover pretty much the entire picture. There's soil here that will cover half of the picture, and the model trains to detect that and to output bounding boxes for that. So we pre-train our object detection model on these new classes for 300 epochs, and then we freeze the weights for this object detection part, the entire transformer pretty much, and then we start training the segmentation part. And so this is the diagram I come up with that replaces the overcomplicated diagram from the paper, and let me walk you through that. So again, we start with just a bare image, and this first part of the model is basically the transformer that we've seen before with frozen weights. So we take the image, we feed that into the backbone like ResNet. The output of the backbone is typically a set of feature maps of different scales, like 25 by 25, the last layer, 50 by 50, 100 by 100, 200 by 200. Typically in DETR, it's an old model, it only takes the last layer, the smallest one, 25 by 25, and uses that in its encoder. The output of encoder, which we usually call memory, is then fed into the decoder along with statically initialized queries to output our query outputs that basically are used for detection and classification and all of that. So this is the part that is exactly like DETR. And then we use it to perform additional pixel segmentation. So how do we do that? So first of all, we have this attention map here, where we take these query outputs, we take the memory, and we multiply them together to come up with these new attention maps. So basically, you can think of this multiplication times this multiplication as crossing out this common embedding dimension. And so the output will look like 25 by 25 pixels times 100 queries times this 8 here. So 8 is because we actually have multi-headed attention. So we perform the same computation 8 times. And for every query, we basically have 8 different attention masks like these. And so we have 800 of them in total. And this is the example of how these attention maps look like. So this is basically the set of weights to where this specific query pays attention to in the image. Then we do a quite weird operation called concatenation and repeating here. So we take memory output, which is again a set of pixels 25 by 25, each with a 256 dimension. We repeat that feature map 100 times, and then we concatenate the 8 attention weights that depict for every pixel where this query pays attention to. We concatenate it with the embedding dimension. So we had 256 embedding here, and after this concatenation, we'll have 264. So we added these extra 8 numbers on top of 256 that we had in the encoder output from these attention masks. And so the full tensor shape at this point will be 100 by 25 by 25 by 264. So you now have 100 feature maps, one for every query output, each with these 8 extra embedding coordinates. And then we perform what is typically called a feature pyramid network, where we basically take these low resolution 25 by 25 feature map and we try to upscale it to higher resolution, looking backwards into our original feature maps of higher resolution and merging them together using convolutions. So the exact process will look something like that. So we take this low resolution feature map, we upscale it to 50 by 50 using bilinear interpolation, which doesn't really add any new information, we just basically enlarge the image. But then we concatenate that upscaled version along the embedding dimension with these feature maps here for every pixel, and we apply a bunch of convolutions, basically fusing the information from the original feature map of high resolution that knows where which pixels are, and we fuse that with our upscaled version of the feature's output, and we perform the same process multiple times. So we apply convolution, then again upscale, convolution, upscale, convolution, at which point we get up to this 200 by 200 resolution, and we consider that to be our mask output. So again, we had the same feature map repeated 100 times, so we get 100 outputs per pixel, which basically says for each of the query in the output, or every pixel will get some sort of confidence score, like what this query, which pixels does it think it belongs to. And so after that, we apply a confidence threshold, so we throw away parts of the masks that have below 85% confidence, and then we perform per pixel argmax. So before this argmax, we actually might have intersecting segments, because two queries might actually sort of detect the same pixels, but we need strictly non-intersecting segments in the output, so we perform per pixel argmax, where for every pixel we decide to which mask this pixel belongs based on which query output has the most confidence score. So looking back at all of these, again, comparing to segment anything model that we looked at before in my previous video, we have this weird attention map calculation that is then concatenated along the embedding dimension to encoder output. And this is the way to fuse this attention from queries mechanism to the original feature map. And we've seen in SAM that in SAM it's done using this modern cross-modality decoder that I guess was not a thing back then, back when DETR came around. So here we have this weird sort of attention maps being concatenated to features, which I guess is quite limited in terms of which information you might pass around in these 8 attention maps. But still, it is something, so it allows you to actually pass some sort of query to pixel interaction information into your convolution. Then we have our typical feature pyramid network that takes this low resolution feature map, which by this point we can already consider as some sort of output of the model. So we can turn that into our mask outputs at this point if we just project this 264 dimension embedding into one confidence score, but it will be low resolution. So it will be 25 by 25 resolution. So to upscale it to the higher resolution, we use this feature pyramid network with a bunch of steps, with upscaling with linear interpolation, concatenation to original feature map, and then convolution to fuse information together. And so the original picture was actually much higher resolution than this 200 by 200. So we need the actual next step to upscale it further. And in DETR for segmentation, that again is done using just bilinear interpolation. So because of this, the masks themselves will be a bit pixelated, which is fine for big objects, but maybe not so fine for small objects. So in later models, there are different techniques to do that even better. And this is the picture from the original paper that tries to explain the same thing of how we get from original image to query outputs to attention masks to the final output. I don't think you can actually understand what's going on in there from this picture. Couple of final notes on pretty much what just happened. So we've talked about Panoptic segmentation task and how it can be applied for stuff and things. And both of these actually were challenging for convolutional neural networks. Because for stuff classes like sky, it's not enough to do local calculation, because it's quite hard to distinguish if it's a sky or, say, water. Just looking at this one piece of image, you actually need to look at other objects on how this particular piece is located with respect to other parts of the image. And convolutions historically were not that good at that, and transformers thankfully are. And for instance segmentation, it's also challenging because now you have to detect variable number of instances per image, and you need to avoid detecting duplicates. And again, in case of DETR for segmentation, we basically piggyback on the object detector part of the model that is trained in exactly the setting where each query represents exactly one object. And the Hungarian matching loss already forces the model to have this one-to-one connection to ground truth. So one query tries to detect one object, and queries interact with each other in the decoder to avoid predicting the same thing twice. And so we basically use the same setting in our segmentation part of the model, where as an output of vanilla DETR, we have these queries. Each of them already has information about the location of the object, and we try to use the same information to now do pixel segmentation, but we already solved the problem of this one-to-one instance detection. And a final word about why this particular attention map concatenation technique is actually good, is because in the attention map within the transformer, we actually get something like pixel segmentation in unsupervised manner. So this is a picture from object detector part of the model that has not seen segmentation labels. It was trained to detect only bounding boxes. And to solve this task, we can see that in in the actual attention maps within the transformer, it already knows how to perform something really closely resembling instant segmentation. So we already see good representations of how segmentation for a cow should look like in this inner attention maps. Finally, let's read the source code of the actual segmentation part of the model. Similar to the original DETR, it's actually in the same repo. You just clone the repository. I will leave the specific instructions on how to install everything and get the dataset in the description. And after doing that, one last step I do is I put a sandbox.ipmb jupyter notebook right at the root of the repository, so that I can import the modules specified in the repository and actually debug through the code of the model interactively. And so this is my notebook. In the very beginning, I have just some imports and standard functions to plot the results, to annotate the classes. I initialize this argparse.namespace object to pass all the arguments, and I just copy them from the output of the actual main.py training script. I have my categories for advanced CoCo with extra classes. So here we see some new names like building, other merged, food stuff, month and merged, and so on. So we initialize the dataset using the function I copied from main.py. Here is how we can get one example out of the dataset, and this is how it looks like. So this is the very first image from CoCo dataset. We can see more classes annotated here. We can see the segmentation image for that, where now each pixel is color-coded to represent a certain object ID, basically, that you can then exchange in the meta information for category ID and actual instance ID. So all the images in CoCo have slightly different shapes. So we have the data loader, which now unites several images into batch. And to do that, we actually need to pad them to the same shape. And from there, we can see this small gray area on some of the images from this padding. This is just to make sure that every batch has images of the same shape within it. But different batches still might have different shapes. And this is totally fine with transformers. Transformers work well with different shapes. Then we build the actual model and criterion, which is the loss and the matcher. And this is how you can actually call the model. So predictions have a bunch of different stuff. So you can see pred logits, that is classification of the object. Pred boxes, that's object detection. Bounding boxes. Auxiliary outputs are used for the loss, and they're basically the same, but for all the intermediate layers. And then we'll have the new one called prediction masks. So our original batch was 800 by 139. And then for the output shapes, we have 100 queries. We have 2 by 100 by 251 logits. So we have 251 classes in this dataset in total. We have batch size of 2. For predicted boxes, we have 100 queries times 4, so 4 coordinates per bounding box, x, y, height and width. And then for predicted masks, we have 2 by 100 by 200 by 260. So this prediction is basically, this shape is a downscaled version of this shape. So before actually computing anything, you would need to upscale it back to the original as well. Let's also take a look at how these mask predictions look like. So each of them is a number. It can be negative, but it's basically a number that represents the confidence score, such that the higher the number, the higher the probability that this specific pixel will belong to this mask. And let's read the actual code of the model. So for that, we need to know what that model is. And this one is called DETR segm. So let me find it. And here it is. So it inherits from an n.module. So we need the forward method. Let's put the breakpoint here. And then I can just debug into the cell where the actual model is called. So I press debug cell, and here I am. So you can see that the samples input is this DETR nested tensor. So to access, and nested tensor basically has the actual images and masks that encode which part of the image is padding and which is not. We can access the actual tensors from here like this. And so we get our batch with 2 images, 3 colors, and 800 by 1039. Next we call our backbone. Backbone in this case I think is ResNet 101. So we positional encoding is also part of the backbone. As an output we get a list of links 4. So here are the shape of that. So the first one is 200 by 260, then 100 by 130, then 50 by 65, then 25 by 33. So it's almost exactly equal to what I was showing you in my diagram. And you can see that embedding dimension goes first up to 256, then 512, then 1K, then 2K. So first we do this input projection, which projects all the embedding dimensions down to 256, and SRC is the last layer of the features, so only this lowest resolution, highest dimension feature map that we got from ResNet. So we call this input projection, and then we get this 256 by 25 by 33 shape that we feed into the transformer. So as promised, we'll not look at the code of the actual transformer. For that, check out my previous video called Reading Data Source Code. So I'm just going to step through this. As an output of that, we have the memory. So the memory is going to be encoder output. It should have the same shape as the input, but it's the output of the first transformer encoder block. So the shape of the memory is, again, 256 by 25 by 33, exactly the same as the shape of input. And then HS is the output of queries. And in our case, we also have outputs of all the intermediate layers. So we have 6 of them, but we only are interested in the last layer, batch size of 200 queries, 256 dimensions of embedding. So then we do the typical object detector part. So we have classification embedding that projects 256 embedding into our new number of classes, 251. We have our bounding box embedding, which projects that using MLP, multi-layer perceptron, from 256 embedding dimension down to 4. And this is the same as vanilla DETR. And this is part of the output as well. And then we have the new thing called this self.bounding box attention. So let's read into that one. So it's called MH attention map. Let me just find it. So here it is, also inherits from an n.module. So let's break this forward method and continue. So coming back a little bit. So as the first argument, we pass HS-1, which stands for the last layer of the decoder output, basically the query outputs. And the second argument is memory, right? So Q is going to be queries, query outputs, and there is 100 of them. And then key is going to be encoder output, basically the same shape as the image after being passed through ResNet. So that's 25 by 33. So first we do this linear projection for Q, and what will just happen can be basically thought of as half of a transformer layer, where we first compute the attention masks, and that's it. That's what we return. So for that we need linear projections for both Q and K. So for Q we just use the linear layer 256 down to 256, so the shape doesn't really change. For key we use this conv2d in a little bit weird way where we have weights for the kernel, and weights and biases. And so self.klinear, let's print out what that is. That's also 256 to 256 linear layer. But instead of applying it as a linear layer, we apply it as conv2d. So conv2d by default will have stride of 1, padding of 1, which means that with a kernel like this, which is basically 1 by 1 kernel, this is the same as applying the same fully connected layer individually to each pixel. So we're not merging information between pixels, we're just projecting each pixel independently. And this is pretty much the same as here. And I guess one way to do that would be to flatten this sequence and then performing the normal matrix multiplication and then unflattening it again. Here they just do that as a convolution to sort of underscore the fact that we're dealing with something resembling an image here. And again, this will not really change the shape of K. So it's still 25 by 33. Then we have this reshape here where we move out the heads dimension. So we have 8-headed attention, all right? And the embedding dimension of 256 gets split between these 8 heads. So final embedding dimension per head will be 32. So now QH shape is 100 by 8 by 32, and KH.shape is going to be 2 by 8 by 32 by 25 by 33, right? Then we have this interesting torch.einsum. So it's basically, again, a matrix multiplication, but here it is written in Einstein's notation for convenience. So really recommend reading up on that. It's really convenient. So basically here they tell us that they have 2 input tensors, one which batch dimension, number of queries, number of heads, number of channels per head. And in the second tensor, we have bunch dimension, number of heads, number of channels per head, and then height and width. And then we turn that into a tensor with some dimensions. And the dimension that are missing here, it's implied that we sum all the coordinates along that dimension, which is a matrix multiplication. So if you stare at it long enough, you'd see that the one dimension missing in the output is C, which stands for embedding dimension per head, this 32 here. So it is the one that is getting crossed out in this multiplication. And from there, we basically get our attention maps. So now the shape of that is 2 by 100 by 8 by 25 by 33. So it has the same shape as the original image, which means we can represent it as an image, as I did here, right? So I can put each of these numbers in this 2-dimensional box and see that it does indeed look somewhat like a cow. And then we have 8 of those for each of the 100 queries. So 8 because we have 8 heads in our attention. Then we just do softmax, dropouts, and this is what we return. So the shape at this point should be the same as before. So then we return from here. So we go to our original data segmentation forward. And after this B-box attention, we'll have mask head. So mask head takes in the 3 first outputs of the backbone. So this will be used for the feature pyramid network to upscale the pixel resolution of our masks. It also receives this SRC projector, which is the input to the decoder. So at this point I realized that I've made a mistake in my diagram. So we feed in encoder input to this repeat and concat module, not encoder output. So basically we have to reconnect this here. So sorry about that. So what is mask head? Mask head is this mask had small conv, so let's find it. Here it is, again, inherits from n.dot module. So let's break at the forward method, continue, print out all the inputs first. So x.shape, that's 25 by 33, and then we have this fpns, which are all the other backbone outputs of high resolution. And then we have this bbox mask that we've just looked at. This is the 8 attention layers per query, 8 attention masks per query. So for each of the 100 queries, for each of the pixels in the image, we have 8 extra attention weights. So we start with this concatenation. So this expand function is a combination of unsqueeze and repeat to basically change the shape of the tensor. Let's just look at all the operands here one by one. So first the expand. So the output shape of this will be 200 by 256 by 25 by 33. So the input to this one was 2 by 256 by 25 by 33, and we basically repeated that 100 times. So this is the repeat operation that I was telling you about, where we take the feature map from the backbone output and repeat it 100 times, once per each output. And then we do this bounding box mask flatten, which again just flattens it along this byte dimension, and you can sort of see the same shape here, right? So 200 by 256 by 25 by 33 versus 200 by 8 by 25 by 33. And then you concatenate along the second dimension, which is this one, which means that you take 256 dimension embedding from backbone output and you add these 8 attention maps to that. And so the output of that will have embedding dimension of 264. So you've concatenated this attention maps to your features within each pixel. So then you have a bunch of convolutions. So layer 1 is a 3x3 convolution with stride 1, then group norm, relu. Layer 2 projects 264 down to 128. Again, kernel side 3, stride 1, padding 1. So we're slowly going down in embedding dimension, right? At this point, X has a shape of 25 by 33 with 128 embedding dimension. And then we have 3 consecutive upscaling blocks. So first this adapter. Adapter basically projects 1K embedding dimension from backbone output to the embedding dimension we currently have, 128. So we apply it to our first backbone output, and we again repeat it 100 times. So this current VPN size will be now repeated 100 times, and it's 50 by 65. So it's roughly twice bigger, twice higher resolution than what we have now in X. So then we have bilinear interpolation. Actually, I've lied to you again. It's not bilinear, it's nearest interpolation, which is almost the same thing. So we're not creating new information here, we just enlarge the image. So the we apply 2x, and the output of just the interpolation, the shape of that is now 50 by 65. And then current FPN has the same shape. And so we sum them together and apply this third convolution. Again, kernel side 3, stride 1, that projects 128 dimensions down to 64. So at this point, we basically have original backbone output with high resolution, enlarged, upscaled version of X. We added them together, passed through convolution, thus fusing information from both of these together. And from here we get an X with the shape of 50 by 65. And embedding dimension has reduced to 64. Then we again do group norm, relu, and then we repeat the same process a few times. So if I just continue to here and print the shapes, so it's up to 100 by 130 in resolution, down to 32 in embedding dimension, and then the final one up to 200 by 260 in resolution, down to 16 in embedding dimension, and then final projection that project these 16 embedding dimension down to a single number that will represent this per pixel confidence score. And so the shape of the result is 200 by 1 by 200 by 260, which means that for each of the 2 images in the batch, for each of the 100 queries, we have our mask predictions, where for every pixel we have some sort of confidence score representing whether a pixel belongs to this mask or not. And so these are the masks that we've seen in the model output. So I can safely return from this debugging session. And the one thing I also wanted to show is the actual loss. So we have this criterion object that is a set criterion. And first of all, we can just call it like this using predictions and targets. And we can see in the output that we have a bunch of losses for different layers. So we have loss cross entropy, bounding box, generalized IUU. And for mask loss, we have the actual mask and dice loss. So we'll look at both of them now. So the actual criterion, set criterion, is defined here. And it has losses for the object detection part of the model as well as for segmentation part of the model. Part of this loss is the matcher object. So let me just start the debugging session and show a little bit around. So the point of matcher is to say which of the ground truth object has a match to which of the 100 query outputs. And so matcher is called Hungarian matcher. We can take a look at it here. But basically what it does is it computes some approximation of the loss that we'll have for any potential matching. And it only uses the bounding box loss and the classification loss. So in this, we will not see any loss related to segmentation. And then it calls this scipy.optimize.linear sum assignment function, which basically chooses one unique matching that optimizes for this loss approximation. So the output of that will be a set of indices that connect the query outputs of the model to the ground truths in this particular batch of images. And so you can see from here that we have 5 objects in the first image, we have 12 objects in the second image. And so in indices object, we'll also have 5 indices which say which queries correspond to which ground truth objects in the first image, and then 12 in the second image. And then we'll iterate over a bunch of losses, including bounding box loss, classification loss, and one of those that we'll read is loss masks. So let's continue to here. So outputs is this entire dictionary with all the predictions of the model. Targets is entire dictionary with all the annotations we have for the dataset. So we get the IDs and select only those IDs that were actually belonging to queries that matched with ground truth objects. So SRC masks, we started with 100 masks in total, and now we are down to 17 per 2 images. So 5 from the first one and 12 for the second one. And then we have the same for the ground truth masks. So we have 17 ground truth masks, and you can see from here that the shapes are slightly different. So we still need to upscale this resolution up to 800 by 1K. So we do that with bilinear interpolation here to get our predicted masks to the same shape. and then we flatten both of these. So after flattening, the shape is this enormous 800k pixels, where we get 800 by multiplying 800 by 1039. So that's where you get this large number. That's basically an entire high-resolution image flattened into one long sequence. And then we compute these losses. So sigmoid focal loss, you can think of that as binary cross entropy that is computed per pixel, because the SRC masks is basically a number from, I guess, -1 to 1, which represents some sort of confidence. And then target masks is actually a number from 0 to either 0 or 1. So it's Boolean, either false or true. So there is no in between here. So cross entropy loss basically computes the loss, like how good are we at classifying each pixel. And the focal loss is basically a modification of that one, which pays more attention to positive than negatives, because we have much more positive than negatives. And then we also have the dice loss. So let's actually read the code for dice loss. So dice loss is defined here. Again, inputs.shape, target.shape. So you have 17 objects and this 800k sequence. So first we take the sigmoid, so we turn our numbers that can be of arbitrary scale into something from 0 to 1. And then we perform this multiplication and sum along the first dimension. So the multiplication basically multiplies the confidence scores with zeros and ones in the ground truth. So the shape of that one is the same, 17 by 800k, where the value of this multiplication is 0, where this part of the image did not belong to this object, and then it is equal to confidence score in the parts that did. And then we sum along the first dimension. So we get an object with shape 17 by 1, right? So we've basically computed the sum over all the pixels for every object. And then in denominator, we just have the sum of all the inputs, so total confidence, and sum of all the targets. And we divide y by the other, which will yield something close to IAU, but slightly different. So this is the same formula in maybe a more familiar format. So this is the dice loss. If you remember, in IAU you have this multiplication divided by, which is basically intersection, divided by union. And then in dice loss, instead of union, you have just the total size of ground truth plus size of the prediction. But directionally, it is almost the same. And then we, of course, reduce everything into single number. And so this was it regarding use of DETR for segmentation. I hope my video was useful. I hope it helped answer some questions, and see you soon.